I erased my board. Much fun on the... Yeah. Welcome to watching your professor pace back and forth before erasing his board. Tune in to see more quality content from my YouTube channel, like erasing other boards. Thanks. Alright, so last lecture we talked about fatigue. This lecture we're continuing our discussion on fatigue. And here we're going to be talking about what's called the endurance limit. Okay, the endurance limit is effectively a yield strength or an ultimate tensile strength for a material by which, if you load a material a certain number of cycles, it can handle this amount of loading. Okay, so here in fatigue loading, so for static failure, we had brittle materials that failed under SUT or SUC, which is the ultimate tensile strength or the ultimate compressive strength. And then you had the ductile materials that failed. They could have either failed in tensile or compressive strength, but usually they failed with the yield strength. For fatigue loading, what we have is all of the types of materials are going to fail in this type of brittle failure based on the endurance limit. Okay? And the endurance limit is ultimately what determines what the maximum strength of that material is. So if you're talking about SUT, SUC, or SY, these values can be determined for a material, for an entire batch of materials. These values do not depend on the loading frequency, do not depend on the loading nature really at all. So these are independent qualities. These are things that we can measure about a material anywhere. You can do a tensile test on an item, very simple. However, this is a dependent quality because it depends on cycles, number of cycles it experiences, and the loading conditions. So the endurance limit itself is a lot more complex than just going and grabbing from a table SUT, SUC, or SY. This is why a lot of companies will insist that you cannot know what the endurance limit is unless you actually test it. Okay? So I'm going to thoroughly confuse you in this class, hopefully, because this is a concept that confused me as a novice engineer. This is not super intuitive. So when we're going to calculate the endurance limit, we're ultimately trying to figure out the strength that our material is going to have when loaded in multiple cycles. Okay? I'm going to throw equation 6-8 at you. Okay? Equation 6-8 says that for steels, which most of our discussion on the endurance limit here is going to be about steels, just FYI. S prime E is equal to one of three values. 0.5 times the ultimate tensile strength if the ultimate tensile strength is less than or equal to 200 kpsi. It's going to equal 100 kpsi if the SUT is greater Oh, that doesn't make any sense. Then 200 kpsi. Okay, and for the metric equivalent, it's 700 megapascals if the SUT is greater than 1400 megapascals. Okay. All right, so what does this tell you? Well, this right here, again, this value does not depend on the loading conditions. As we just discussed over here, the endurance limit depends on loading. We have to know the number of cycles. We have to know how it's being loaded. And if we don't know those two things, what does this even mean? Well, this is a starting variable. Okay? This is a variable that we're going to use in an equation to figure out our endurance limit. All right? So this is a nominal endurance limit. Not actual, because again, this does not depend on loading at all. This is just an estimate. It's a number that somebody threw out there. Okay? So, we now know this. The actual endurance limit is given by equation 618. And this is an estimate. So this here is a nominal value that we throw out for calculation's sake. Now we're going to use this nominal value to calculate an estimate. It is ultimately stated that the endurance limit should always be tested. You can't actually know what it is unless you test it. You can measure this value directly. Because this can be tested, this is a testable value, but this value is used to find this value. So yes, that does look like the endurance limit, but no, that's not what the endurance limit is. The actual endurance limit is, the endurance limit, SE, is equal to KA, KB, KC, KD, KE, KF, S prime E. Okay, so we use this value here, which is this value right here, to figure out what the actual endurance limit is, or what our estimated actual endurance limit is going to be. And we have all of these modifying factors that depend on loading conditions, that depend on number of cycles, that depend on how it's loaded, depend on the surface condition of the material, depend on the temperature of the material. You can use every single one of these, and each one of them modifies our estimate, our estimated nominal value, to find the estimated actual value. A little bit confusing, but again, you use this here to find this. This is not your endurance limit. That is only an estimate, a nominal value that is used to find the actual one. Do not give me that as your endurance limit. Okay? This is the value you need to give me. If I ask you for an endurance limit, it's this. Alright, so each one of these has either a formula or a table of values that are associated with it. And again, this is why I love Shigley's book. If you ever have a condition where you're dealing with fatigue loading and you need to know what your estimated endurance limit is, and you don't just want to throw a bunch of specimens into a physical testing situation, have them cyclically loaded, and then figure out what each of these values are, great, you know. Coming up with an estimate will give you a great place to begin to start those tests. It reduces the number of tests, reduces the number of hours that are required to perform these tests, the amount of money to do this test. If you know how to do this, you save your company a lot of money. Anyways, so here Ka is equal to A times SUT to the B. Okay, and the values for that are given by table 6.2. Okay, you can find A and B values from table 6.2. It depends on what kind of a finish it is. Okay, if it's ground, what that means is that you had some kind of a rough surface, it was cut, and then that's your surface, is just ground. You may have machined, which means it was drilled or it was planed. You have hot rolled, or you may have just a straight forged material. Depending on how it comes out, most of the time we're going to be dealing with hot rolled probably, parts coming straight out of it. Occasionally you'll deal with machined. But in that case, then you just multiply these factors by this, plug it in for Ka. That's already a huge factor, and we haven't even talked about the number of cycles yet. Okay, Kb is a factor that depends on the size. So this depends on finish. This depends on size. For Kc, this is where you're talking about the modality of loading. Is it in tension? Is it in compression? Is it in bending? Is it in torsion? Okay. For D, this is where we talk about temperature. For E, this is where we talk about reliability. And for F, this is where we talk about miscellaneous factors, such as you may be dealing with case hardening, parts that come in with some corrosion, parts that have been electrolytically plated, etc., etc. So these are all factors that affect this endurance limit. And this endurance limit ultimately states, on the SN curve, this endurance limit is that infinite lifespan. Okay, so this is really pertaining to items that have a lifespan greater than 1,000 cycles, 10,000 cycles, 100,000 cycles. Okay. So this is the endurance limit, and you can use the formulas and you can use the tables to find each of these variables, plug it in here. Now, what good does the endurance limit do for us? Well, as I mentioned before, for static failure, what we're looking for is we're looking to have the yield strength or the ultimate tensile strength or the ultimate compressive strength. That is going to be our failure condition. Here, okay, I'm going to diagram out the process for determining static failure. Okay, so just kind of a review of what we talked about last week. The first step that we did was we determined geometries. You got to know what the part looks like. Okay, once you know what the part looks like, then you plug in your loading and you figure out your loading. This is where you do your free body diagram. What are the moments being applied to the system? What are the forces being applied to the system? Okay, and once you know this, then you can also determine whether you have axial forces, shear forces, bending moments, and torsional moments. Okay, those four things are what you have to figure out when it comes to loading. Once you know your geometries and your loading, this is when you can figure out your stresses. Remember, stresses depend on loading and geometries. Okay, you come up with your stresses, and for your stresses, you're going to have your normal stresses, your shear stresses, your bending stresses, and your torsional stresses. But then all of these are going to combine into sigma x, sigma y, sigma z, tau yx, or tau xy, tau yz, and then tau xz. Okay? You combine each of these based on their directions to find what these values are, which is part of the stress calculation. Once you know these, then you go find your principal stresses. Sigma A, sigma B, sigma C. Once you know those, you rank them sigma 1, sigma 2, sigma 3. Okay, so to recap, start with your geometries, come with loading. Once you figure out your loading, that is your axial forces, shear forces, bending moments, torsional moments, then you calculate the stresses directly from each of those loading conditions. Normal forces, normal stresses, shear stresses, bending stresses, torsion stresses. You figure out what the directions are. You add them together to get what is your sigma x at a certain location. Sigma y, sigma z, tau yx, this. You plug these into the equation to calculate for your principal stresses. Sigma A, sigma B, sigma C. That's that really long three-dimensional equation that I gave you. You then order them, sigma 1, sigma 2, sigma 3. Okay? Now, once we have our principal stresses, we can plug this into our static failure theory. Okay, whether that's distortion energy theorem because it's a ductile material, whether it's brittle Coulomb Moore because it's a brittle material, whatever it is that the failure theory is, you'll end up plugging it into that. Okay, and then this gives you a safety factor. So that's the process of doing a calculation for static failure. That's what we did in class last week. Okay? Now, side note, let's say you're designing a part. You start here. You're given a safety factor and you say, I want this to be able to handle 2 times loading. Okay? Now, sometimes what you can do is you can go back here, change the material type and have it fit. Sometimes you can't. Sometimes you have to go all the way back and you have to modify the geometries, go through this whole process again. Everything up to, well, really here can be done by SolidWorks. If you plug in the geometries and the loading, this part can be done by SolidWorks. It spits out a von Mises stress. Von Mises stress is used in the, it's a ductile failure condition. It goes with the the DET method, distortion energy theorem method. Okay. Once you figure out von Mises method, then you get your safety factor really quick. So as long as you know what these two are, this part can be handled by SolidWorks or by a finite element analysis software. That's super awesome. You know, get through that. Save you some math. But this is the math that has to be done by hand. It has been done by hand for over a century now to figure out and safely design components. Okay? But that's just for static failure. What's the difference now between this and fatigue failure? Okay, I'm not going to list out every one of these steps because it's the same for this. But you start with your geometries. You determine your loading. You calculate your stresses. Same way. You have to list out axial loads, shear loads, bending loads, torsion loads, how they correspond to an axial load will create a normal stress. Shear load will create a shear stress. Bending load will create bending stresses. Torsional load creates torsional stresses. Okay? Same way. Once you come up with your stresses, you add them together to get your 6-state stress condition. Which is what this is. That's just a fancy way of doing it. It's, 6 states. 1, 2, 3, 4, 5, 6. Okay, once you know your 6 states, sigma x, sigma y, sigma z, tau x, tau yx, tau yz, tau xz, then you calculate your principal stresses again. Well, that's awesome. So far, this seems really Straightforward. I mean, we're doing the same thing again, right? Is this easy? Well, then you go into your fatigue failure theory. But the problem is, fatigue failure theory requires a calculation of the endurance limit. So there is one extra step that is needed for fatigue failure. Okay? I told some of you last week that static failure is great, but fatigue failure is this much more, because you have to understand what the endurance limit is. You have to be able to calculate it, or you have to be able to read it from a graph. You have to be able to figure that out. What is the endurance limit for that material, for the number of cycles you're trying to figure out? You plug in the endurance limit because the formulas that are used for fatigue failure require the endurance limit. They may also require yield strength. They may also require ultimate tensile strength or ultimate compressive strength. You may need to know all of those factors in order to plug it into a fatigue failure theory. Once you have this, this tells you what your safety factor is. Okay, so it's very similar process between these two, but you do have to do an extra step of figuring out what the endurance limit is. Okay. So this is fun. This is fatigue. Fatigue is, in my opinion, it is the hardest calculation to do. Now, we were able to do the static loading last week. We were able to do it pretty effectively, pretty quickly. We got it done in an entire class, although I had to run a little long. You can watch that video. I posted it online. It's a little bit longer than 50 minutes. But we were able to do that in 50 minutes in one class period. We were able to step through everything. This does require one extra step, but this is it. That's the extra step that's required. You do have to go through a different set of failure theories because there's different formulas associated with them, but that's it. It is the same process, where it just, instead of only plugging in SY or SUT or SUC here into the static failure theory, you're also plugging in the endurance limit. So fatigue is not that hard if you understand what you're doing and if you understand what the endurance limit is. Okay? Remember, it's the estimate I gave you. If you ever were to test the endurance limit that you test is exact. It's not that first estimate where it doesn't depend on loading conditions at all. It is an exact one that you can use for any of your calculations. You can plug it straight into this as your endurance limit. No modification needed. Okay, so this could be a tested value. If you're going to calculate it by hand, you're going to use that second formula that I use where it's got all those modifying factors. Or, I believe it's section 6.4 in this book. No, section 6.6? Yeah, section 6.6 that talks about crack growth and loading, and I'm not expecting you to know that material because, quite frankly, that stuff is kind of gross. But for all of this, for all of the discussion that we've had so far, this assumes a fully reversed loading. Okay, so keep that in mind. This is fully reversed, which again means it goes from your stress element goes from tension all the way down to compression, all the way back to tension. It's a fully reversed cycle because it experiences the same magnitude of tension and compression loading. What we're going to be talking about in our next video, which I may either post this week or next week, just to finish out fatigue loading. But what we'll be discussing then is how do you handle it when it's not fully reversed. It's just a different way of calculating it. And it does have some effects on the endurance limit. The endurance limit is actually less small for non-fully reversed loading. Like I said, this is the worst condition of loading you can possibly apply to something. Okay, so I'm going to be giving you, I said I was going to give you 3 videos this week. I'm actually going to be giving you 2 more videos this week. One of those videos is going to be on, I'll give you another example of static loading. One of those videos is going to be, I'm going to give you a further discussion on fatigue when it comes to non-fully reversed loading. And I'll explain what the difference is between fully reversed and non-fully reversed is. Everything that I've told you so far, this is fine, great. I'm just going to teach you a little bit more that has to do with the endurance limit. So I guess I'll see you in those 2 videos when I post them. Not really sure when I'm going to have time to do it. I was thinking maybe tomorrow morning, maybe not. So it just depends on when I have time. But I'll get these 2 videos to you as soon as possible. Heck, I may even get them to you today, because I feel ambitious and it's machine design. I love machine design. See you later.